Welcome. Today I'm going to talk to you guys about Newton's second law of motion. It's really the mathematical underpinning of all of classical physics. It's kind of a big deal, if you will. Newton's first law is the basis, the foundation for it, the law of inertia. If you remember, that law of inertia talks about three things. It talks about masses as being a measure of resistance to a change in motion. It talks about forces being the causes of changes in motion. And it talks about accelerations being the changes in motion, right? And so what he did, and this is really genius, is he put the three together in a formula. And he said that for every acceleration that's produced, it's related to the force that's applied that creates it, and also related to 1 over the mass. And so what ends up happening is, you can look at it this way. The acceleration that's produced is equal to the force that produces it divided by the mass that resists it. I'm going to say that again just to make sure. An acceleration that's produced is equal to the force that produces it divided by the mass that resists it. So let's use that idea just for a second to come over here to our golfer. Now our golfer has a small mass golf ball, and he is able to apply a force using the golf club to the golf ball. Now, as I said, the golf ball's mass is very small. If his force is a certain amount, you can see that it's going to should have a large effect on the golf ball. In fact, the golf ball gets a large acceleration because its mass is so low. If, for example, and I don't know why you would do this, but if the golfer with the golf club was able to apply the same force to the back of a large truck like this, obviously the truck has a large mass and therefore a large resistance to a change in its motion. If that same force is applied, you're going to see there's a very small acceleration that results. So we can see mathematically that these three things are related. And in fact, the way that we remember it, because it's easy to remember, is this way right here, that a force, in this case a net force, is equal to the mass that it's applied to multiplied by the acceleration that it produces. Now notice the force and the acceleration are both in the same direction. So if you have a guy like this right here who sees this cart on wheels and decides that he wants to move it, he can apply a unbalanced external force. Right? He's coming at it from the outside. He's not inside the cart right now. And he applies a force. Now there might be a small frictional force going backwards, but let's ignore that for right now. There's also a normal force supporting it and a gravitational force pulling it down, but those are verticals and they cancel each other out. So we're not worried about that either. So what ends up happening is this net force is really just the push that he gives it. If we ignore friction, that's really just it. And so he applies this net force and it causes the cart to change its motion. Now let me ask you a question. Would it make sense if you were to push in this direction and then for an acceleration in that direction to be produced? I think you'll agree there's no way that that can happen. If you push something in a certain direction, it must change its motion in that same direction. And so what ends up happening, is, that was terrible, is that every acceleration that's produced, like so, by a force must go in the same direction as that force. So again, the force and the acceleration, both in the exact same direction. Hopefully that makes sense. We're going to use the direction of the force, of the net force, to be able to figure out the change in motion that occurs in the direction that it occurs later on when we do more diagrams. This will also become important later on when I twirl a bucket on the end of a string, because I'll ask you a question like this. What if I'm holding the string here, the string's going out and then connecting to the bucket, and then the bucket is moving around, and of course the string is connecting my hand and the bucket. So it's like the radius of a circle almost. I think you can see that the reason why the bucket travels in a circle is because I am applying a force through that string. So later on when I ask you, okay, now that you know where the force is, can you tell me which direction the acceleration must also occur? And you're going to see that the acceleration occurs in the same direction, both towards the center of the circle. If you want something to move in a circle, you have to accelerate it towards the center. And we'll talk about that. We have a whole unit based on that, so that should be good. Okay, just a couple other things real quick. If the formula is F equals ma, then we now know what 1 Newton actually means. 1 Newton is actually equivalent to 1 kilogram times 1 meter per second, or just meters per second squared. So 1 kilogram meter per second squared is equal to 1 Newton. So at this point, you now know where that comes from. And if I asked you the question, could we use this unit instead of this unit? The answer to that is yes. Technically, we could totally measure forces in kilogram meters per second squared. But who wants to say that all the time? And we really have to do a lot of this. And so it's much easier to use the unit that we can derive based off of this. And that's named for Newton. It's kind of nice that he's able to get that recognition since he was kind of the father of classical physics. Okay, one last thing, and that's this one right here. You heard that to find the weight of an object, you have to take its mass and multiply it by the acceleration due to gravity, negative 9.81 meters per second per second. So here's the weight, right? Weight is equal to the mass times the acceleration due to gravity. And the negative just means downward, right? So there we go. So what does this formula look like? This is the mass-weight conversion right there. And we can use it to take a mass and convert it to weight, or take a weight and convert it to mass if we wanted to. But where does this actually come from? I showed you that great graph the other day, but in reality it comes directly from Newton's second law of motion, solved specifically for gravity. So the net force is equal to the mass times the acceleration. But the acceleration, when gravity is concerned, is the acceleration due to gravity. So this is actually a little g right here. So this formula right here and that formula are really exactly the same, only this is the mass-weight conversion. And this one is important enough that I wrote it separately on your formula sheet. So you should be able to take a look at that. It's a special form of the second law, right? It's just the second law taking into account gravity instead of just any generic acceleration and force. So that wraps it up. If you have any questions, please let me know. Thanks.